So in this lecture, I want to talk about a new reaction, which is pretty exciting. So let's get that in front of us. The name is the Diels-Alder reaction, and it's named after two prominent scientists that discovered it. Anyway, let me just take a second and hold for applause, as this is probably one of the most revered reactions, certainly, and rightfully so. It's an exciting reaction that forms, and it really kind of just accomplishes a lot of the challenges that we were trying to, a lot of the challenges we have when we're trying to make molecules. It sort of handles all of them without issue. So this is, we're going to actually focus on this single reaction for the next few lectures. And the general reaction is as follows. In the general reaction, we take an alkene and we react it with a diene to form a cyclohexene. So at the very least, we should recognize that whenever we're trying to propose a product for this reaction, we should have a cyclohexene be present. Now, what's cool about this reaction is, as I have indicated over the arrow, to get this reaction to occur, we actually just maybe need heat. We could probably get away with some light in some cases. But in a single step, without reagents, without added reagents, we form two CC bonds, and it turns out with control of stereochemistry. All by taking an alkene and mixing it with a diene and perhaps applying heat to the reaction. And so let's just get this out of the way. This thing is a diene. It's not a dialkene, even though it's sort of just a dialkene. It's just people call it a diene. And everybody loves the old adage, if I've got a person, well, no, they're not happy. If I've got a person that's attached to the diene framework, they're always saying, help, I'm dying. Okay. All right, starting off on the right foot, help, I'm dying, right? So they're sad, they're dying, in fact, it actually works better if they're upside down. So there's the dying upside down. Now the person's really sad because they're dying. Okay. And t-shirts abound for chemistry clubs across the country. Okay, so what we do is we take these two things, we mix them together, perhaps with some heat. We form two new carbon-carbon bonds along with a fairly important ring structure, the six-membered ring. So let's go ahead and just break this reaction down a little bit by considering the mechanism. It turns out the mechanism's pretty straightforward. What we do is we just sort of have arrows connecting where we're going to move the double bonds around. So I've got an arrow connecting a star to a square atom. And I show that by having the arrow go in the space between the star and the square atom. Perhaps you want to add some dots to this, and maybe down here as well, because down below we could have the square connecting with the star by having the arrow move in the space between there. But don't forget that third arrow showing the movement of the pi electrons, and that gives rise to a structure like this, where here are the squared carbons and then the starred carbons are on the left. Okay, but we can relax this geometry and let it come back down to something that we're more familiar with, and that's just a six-membered ring with a double bond in it. So that's the mechanism. Maybe I'll redraw it really quickly so that we can see it without the all of the things added. And I'll put a plus sign just to show that we're mixing those two things together. Now what's cool about this is the arrows can actually go clockwise or counterclockwise. Whoop, I have them going the same direction. They don't have to go the same direction is the point of this. So we could have them go counterclockwise and we get the exact same outcome. Okay, turns out this is an example of a pericyclic reaction. A pericyclic reaction. Okay, now pericyclic reactions are a special class of reactions where, let's write it this way, in a pericyclic reaction, we usually have no intermediates. So we say no intermediates are involved, and that's another way of saying we have a concerted mechanism. We have a concerted mechanism, or a one-step mechanism / reaction, however you want to think about it. We don't have the buildup of like carbocations. We don't deprotonate anything to make an anionic intermediate, which then looks for a positive charge. We sort of have these interacting pi systems. So in a pericyclic reaction, pi systems interact to rearrange electrons. Now, typically, in a pericyclic reaction, we start with more pi bonds, and so we start with a bunch of pi bonds. We rearrange the electrons to get out fewer pi bonds, but more sigma bonds. So we often trade unstable pi bonds. And I'll mention that. I'm going to write unstable in here. So we often trade unstable pi bonds for more stable sigma bonds. Now there's two principal components in the Diels-Alder reaction. And we say these are the reactants of the DA reaction. If you don't mind, I'm going to start calling the Diels-Alder reaction the DA reaction. Okay, there's two reactants. We've already mentioned the hilarious one, and that's the diene. The diene is a system with two alkenes, and the two alkenes are separated by a single bond. Now this is the only framework that will, I mean, we can make some of these triple bonds, sure, but we can't have like, I'm going to be careful here. We can't kind of move the double bonds further away from each other or closer to each other and expect the same type of reaction to occur. Excuse me. So the diene, it turns out, needs to be a 1,3-butadiene, where if we look at this structure, hopefully you can see the diene is two alkenes. The buta means 4 times carbon, 1, 2, 3, 4. And the 1,3, because the alkenes start at C1 and C3. So if we look over here, we've got C1, we start an alkene, C3, we started an alkene. If we wanted a number from right to left, we get the same outcome. We would just start at the end being 1, 2, 3, 4. So in this core system, we can only have, this is the only kind of core system that we can get to react by way of the Diels-Alder reaction. So it turns out that other systems that look like this just won't work. So if we have something like this is a 1,4-butadiene. And if you have this, it is not a diene for a DA reaction. It could react as the other component perhaps, but what we're considering right now is the diene reactant. Okay, so the other thing about the diene reactant that's kind of interesting is its conformation matters. So the conformation of the diene is critical. That is, when we have a diene, we can actually take the diene and undergo free rotation, not about the carbon-carbon double bonds, but about the carbon-carbon single bond separating those two double bonds. So let's do a free rotation. If we do a free rotation, we could spin one of the alkenes out and away from the other one. Now, what I like to do is keep both of these structures in mind, but we want to note that this one on the left is reactive in a DA reaction, and this one on the right is unreactive in a DA reaction. Now, it might serve to react with another diene, but for the diene itself, we have to make sure that we're in the conformation on the left. Now, this left conformation is called S-cis, the S-cis conformation. Why is it called the S-cis? Well, if you look, I'm going to take this diene and I'm going to put like some H groups or some R groups on the carbons that are attached to the single bond. So those carbons that are connected by way of a single bond, the internal carbons, if you will, those are attached to two different things. On one side, they've got the carbon group that they're double bonded to. And on the opposite side, they have the thing they're single bonded to, either a hydrogen or another R group. Now, what I'm going to do is I'm going to draw a line right here, kind of right along that carbon-carbon single bond, and I'm going to make note that the two alkenes are on the same side. Now, if they're on the same side, that's sort of cis, right? Cis meaning same. Now, we could draw an alternative one that is S-trans. And I'll get to what the S means in a second. But we could consider a trans-like relationship using the same analysis, where now I've got one of the alkenes flipped away. So if I draw a sort of dashed line across the single bond separating the two dienes, I could have an H and R group. The H and R groups are now on the opposite side. The alkenes are now on the opposite side. So we say that this is trans. Well, it's not exactly trans, and the top one is not exactly cis. What we're saying is that they're sort of cis, or sort of trans, but that's not really what the S stands for. I believe the S stands for pseudo-cis and pseudo-trans. So S-cis equals, and you're like, wait, pseudo? I know pseudo. Pseudo starts with a P. Well, let's just stick with what people do. So this is pseudo-cis conformation. Now, it's not really cis because it's a conformational isomer, and cis means these things can't freely rotate. And it's also not really cis or trans because that implies kind of the arrangement of things, the configuration of things about a carbon-carbon double bond. But if we put the S in front of it, implying pseudo or fake cis and fake trans, we can at least get the idea. Now, so it's not real cis or it's not real trans, but it is important to recognize that even though we can interconvert between the two, it's the S cis that's the reactive conformation of the diene in the Diels-Alder reaction. Okay, so that's an important feature of the diene. Now let's talk about the alternative structure, the alkene reactant. Well, that has a special name, the alkene reactant, or the monoene. It's not called the monoene, and really I'm the only one that ever calls it the alkene. I'm just trying to keep things clear. That is the dienophile. The dienophile, that which is diene loving, right? Loves dienes, or has affinity for dienes. It might be more appropriate, but whatever. We can get emotional about this. And so the alkene reactant is just simply an alkene, and it can be part of another multiple alkene system. It's usually not part of an aromatic ring, though it can be. And so this is just some alkene, I guess, is what I'll say. And so the important thing to kind of take away from the alkene reactant is that it is called the dienophile in the context of the Diels-Alder reaction. Okay, so those are the players in the Diels-Alder reaction, the diene and the dienophile. Let's go ahead and now ask some deeper questions about this reaction now that we've been at least introduced to it in some degree. We could say, why does the DA reaction occur at all? Well, you know, that's a good question, because there's no charges, there's no polarity, there's nothing kind of special that's activating this reaction to occur. It's just a bunch of carbon-carbon double bonds that are sort of spaced around appropriately. Well, we can start with the thermodynamics before we get into how these things sort of arrange in transition-like structure. And we can just say, in general, the sigma bonds formed are more stable than the pi bonds lost. Okay, so the sigma bonds formed are more stable than the pi bonds lost. And more specifically, in a Diels-Alder reaction, we lose 2 pi bonds to form 2 sigma bonds, where sigma has this sort of notation to it. Now, if we look at our starting materials, our dienophile and our diene shown, we've got collectively 3 pi bonds. And then when the reaction proceeds, so I can show the mechanism, when the reaction proceeds and we relax the geometry, we now have 1 pi bond and 2 new sigma bonds. The 2 new sigma bonds I'll highlight in green. They're right here and right here. And then the pi bonds that are lost are, I guess it's this one and this one based on this arrangement, but we could have either one of the 2 diene pi bonds getting lost. Now that's a thermodynamic argument. That is to say, that's looking at where the bowling ball is relative to the floor. When we start the reaction, we seemingly have the bowling ball on the shelf. When we bring it down to the floor, when the Diels-Alder reaction occurs, because we get to a more stable molecule, a more stable arrangement of those species. Now, that is a good thermodynamic argument, but a kinetic argument or some sort of transition state argument is also critical. And the transition state argument allows us to see why the reaction would occur. Typically, when we look at transition state arguments, we like to think about dipoles, polarity, charge. Charges attracting with one another. We don't have that here, right? Everything has the exact same electronegativity, and we haven't added any heteroatoms to induce any dipoles formation. So the transition state argument for the Diels-Alder reaction really is the same as the transition state is all the time. It's just now we don't have charges, and that's orbital overlap. So orbital overlap forms new sigma bonds from the unhybridized p orbitals in the pi bonds. And that's the pi bonds of the starting materials. Okay, that's a lot of words. Let's go ahead and draw some pictures. So let's just remind ourselves of a sigma bond and a pi bond, right? A sigma bond is going to have head-to-head overlap of usually we consider distorted or hybridized orbitals. Where we consider in these hybridized orbitals, we've got kind of the lobes are no longer of equal size as they are in unhybridized p orbitals because they have some s character to them. We then overlap directly head to head, that is the larger lobes kind of find a way to interact and make a strong interaction. So these are strong bonds. Sorry, I have to make a new page here. These are strong bonds. I'm about to draw two unhybridized p orbitals that are overlapping in a side-to-side fashion to give rise to a pi bond. Sorry, I just want to make sure I have enough pages so I don't have to do that once. So pi bonds, and it's the sigma bonds that are strong. Sorry, I got distracted there. Pi bonds, these are weaker. We've talked about these. In pi bonds, what we're going to do is we're going to take two atoms that are already sigma bonded and consider having parallel p orbitals, each with electrons, do side-to-side overlap. Now we can actually allow those orbitals to lean into each other so they can achieve the side-to-side overlap. However, the picture gets to be a little complicated, so I use these side-to-side lines. Now, what I want to do is consider an opportunity for our diene and our dienophile to react with each other. So what I'm going to do is I'm going to draw my diene. Well, let's do it this way, so you can see what I'm trying to accomplish here. And this is going to be considered like the orbitals in the Diels-Alder reaction. So going back to the Diels-Alder reaction, we have a diene and we have a dienophile, and those have pi bonds. Okay, I mean, we've got 4 unhybridized p orbitals for 2 times our pi bonds. And that's our diene interacting with the orbitals in our dienophile, which has 1 times pi bond. And these orbitals are supposed to overlap to form a new pi bond across these back 2 carbons in this case, and then a head-to-head overlap of orbitals in the new sigma bond. Well, this is a pretty ugly picture. But it at least allows us to see what we need to accomplish. We could do a better job of drawing it, though. Let's consider an alternative perspective. In this alternative perspective, what I want to do is consider the orbital arrangement of these things and how they can kind of approach each other and how a reaction can actually occur between a diene and a dienophile. So I'm going to first consider my diene. Instead of this flat structure, I'm going to rotate it, and I'm going to draw the pi bonds. Okay, so what I'm going to do is I'm going to take, here's my diene, I'm going to take it and twist it this way, okay, so that it has some sort of flat perspective to it. We're going to get really used to drawing these things, but to start, it's going to look weird. So I took the diene and I rotated it like this, and then drew it with a little bit of an askew so that we could see all of the atoms. But what I'm trying to do is show it like flat, perpendicular to the piece of paper, but also show all of the same atoms. Okay, so it's like a perspective drawing, you know, like the train tracks going into the cave or something like that. Okay, it's a perspective drawing. Again, I'm pausing a little bit so you can catch up and kind of like sit here and think through this. But this will allow us to draw all of the p orbitals more successfully than we could in the upper left-hand corner of the screen. That is, now I can just draw the p orbitals kind of going up and down. So these are moving parallel to the piece of paper now. So I have 4 p orbitals, and these are supposed to represent the 2 pi bonds. So I have my 2 pi bonds with my 4 p orbitals. And then we could, you know, we could put electrons in here if we wanted to. Sure. Okay, we've got some electrons, just 1 electron each, which I show as these kind of spin up and down thingies. These are my electrons. So this or this is an electron. Now what I want to do is add that to a dienophile. If you notice, I've tried to draw this such that my dienophile is parallel to the back bond. So this is also kind of taking the alkene, the dienophile, and instead of drawing it flat, I'm drawing it like this, so that I can see both of the p orbitals that form the pi bond of my dienophile. Okay, so what we have here are kind of 2 things that need to interact to form head-to-head overlap of orbitals so that we can forge our new sigma bonds. Okay, now this perspective drawing is going to allow me to better see how these things orient and arrange themselves. So what we're going to do is allow the diene and dienophile to interact. Okay, so what that looks like is we're going to once again consider our perspective drawing, except I'm going to avoid the electrons. I'm just going to draw the p orbitals, and I'm going to allow the diene to sort of swim underneath. It could go on top, but imagine I've got my diene right here. I think I said diene. I meant to say dienophile. Sorry. I have my diene up here, and it's flat, but it's tilted a little bit. Maybe I'll draw it like this. So I've got one end and the other end, and there's some p orbitals around my knuckles here. Now coming in underneath is the diene. So it's going to come underneath instead of just bumping into each other, right into each other. The diene's going to kind of duck down, come underneath, and dock in. I like to picture like a spaceship docking. So when we dock, we can allow head-to-head overlap to occur between the diene and the dienophile. So without rehybridizing the orbitals, I'm going to consider the perspective drawing where I have all of my orbitals. Now I'm going to have the dienophile, the dienophile. That one's going to reach a little bit. Now overlapping and forming new sigma bonds. I'm going to highlight that here. What we have here is the formation of head-to-head overlap and sigma bonds. So we have head-to-head overlap, from the dienophile coming in underneath and docking with, like it's coming into a spaceport, I like to think. And then the orbitals at the end of the diene kind of dock in, clamp in, and that's how we allow the diene to come in and actually form the two new sigma bonds. Now, what about the p orbitals that aren't involved? This p orbital and this p orbital. Okay, so around my knuckles, we had p orbitals here and here that forged the first two pi bonds. So what are they going to do? Well, they look at each other. Okay, they each have their one electron that they're contributing to the pi bond. They look at each other and they say, well, those two folks over there are kind of bonding and making sigma bonds. That looks like a good situation. And then they're like, but now we don't have anybody to bond with. What should we do? And they both look at each other and they give each other a high five and they're like, let's just pi bond in the back here. So they're pi bonding back here, and we can kind of see the formation of that new pi bond occur because we have two unhybridized p orbitals left over after the dienophile has docked with the edges of the diene. So that's our new pi bond. It's like those orbitals haven't moved. Now they redistribute electron density so that spins can match and that sort of thing. But the orbitals will now form a pi bond, and that's that back double bond in the cyclohexene. And so what we do is we can actually draw this like this, where we have our pi bond in the back and our new sigma bonds as part of the cyclohexene system. Okay, so that's how the Diels-Alder reaction occurs from an orbital perspective. Again, we're not allowing opposites to attract positives to find negatives, but instead we're looking at the opportunity for pi bonds and their instability to be dealt with by forming sigma bonds instead. In the next lecture, we'll look at the implications of this approach of the dienophile into the diene, particularly with how it has to do with the stereoisomer that's predominantly formed, preferentially formed as a result of this reaction. Okay, have a great day, everyone.